if you do the inverse matrices, you get A. Okay? Now, determinant of AB is determinant of A times the determinant of B. Okay? And this extends if you have A, B, C, D, E, F. Whatever the determinants are of the product is that, just by the associativity of multiplication, okay, and matrix multiplication, okay? So determinant of you could group it like this. And since the product of two determinants, A, B being the product, the determinant of the product of two matrices is the product of the two determinants. This is a matrix, and this is a matrix. A, B is a matrix, C is a matrix. So the determinant of this has to be determinant of A, B times determinant of C. Is that clear? That makes sense? And you want to be able to think like this because it's important. And of course, determinant of A, B is determinant of A, determinant of B, and that's then multiplied by the determinant of C. Because you're applying the fact that the determinant of a product is the product of the determinants. You're doing it twice. And et cetera. So determinant of product, any product of matrices is a product of their determinants. So, determinant of A is just a product of the reciprocal, of the inverse determinants, okay? Determinants of the inverse elementary matrices. And the determinant of any of the elementary matrices is the reciprocal of the determinant of the elementary matrix. Okay? If you go back, if you multiply matrix by 3, an elementary, multiply the identity matrix, multiply a row of the identity matrix by 3, okay, the determinant is going to end up 3. Real easy to see that because one of the numbers in your diagonal will be 3 now. Okay? And the determinant of the elementary matrix is 1/3. So the determinant of the first type of elementary matrix is the reciprocal of the determinant of the elementary matrix. Now the third type of elementary matrix was one where we added a multiple of a row to a column, of a row to another row, and the determinant was 1. Well, you do the same thing with the opposite number, and you get another matrix whose determinant is 1. That's your inverse. So, you know, that 1 is a reciprocal of itself. If you switch 2 rows, the determinant's -1. That's self-inverse. If you switch the 2 rows again, the determinant's -1, and -1 is the reciprocal of -1, right? So we then easily conclude that this is the reciprocal of the product of the determinants of the elementary matrix. And now, let's see, I gotta do a little heavy moving here. So the question is, we're gonna use this. Okay, the determinant of this matrix is 1/2. Determinant of this matrix is 2. The determinant of this matrix is 1. Determinant of this matrix is 1. Determinant of this matrix, where I multiply the second row by negative 2/11, is negative 2/11. I mean, you can see it. That gives you negative 2/11. That gives you 0, right? You get determinant. And here your determinant is negative 11/2. Okay? And then you're adding a multiple of a row to another. Determinant's 0, determinant's 1, determinant's 1. Okay? So determinant of E4 through E1 would be determinant of A inverse. That's 1/2 times negative 2/11. Negative 1/11. And the determinant of E1, E2, E3, E4 inverses equals the determinant of A, since the product of this matrix is A, right? It's 2 times negative 11/2, or negative 11. Okay? Now, what's the determinant of this matrix? Minus 21 or negative 11, which you can do in your head easily, but I thought I'd write it out. Okay? So it worked. Right? Now if you had a 10 by 10 matrix, well, now you know every time you multiply a row by a number, you're going to keep track of that number. Okay? Anytime you switch 2 rows, you're going to keep track of a negative 1, because those are the determinants of the elementary matrices, which have a product that equals the original matrix. So then you do that reduction, which will take a while, but you can reduce a 10 by 10. If you get the arithmetic right, you can reduce it an hour. Okay? Or afternoon if you're slow, or a day if you're even slower. As opposed to the lifetime it would take to do the 3 million 2 by 2 matrices, actually 300,000 2 by 2 matrices times the coefficients that you would need to do it by the definition of the determinant. Okay? Make sense? So if you have a computer doing it, well, a computer might take a little while to do 3 million, coefficient times 2 by 2 matrix, right? 300,000. But you're going to end up with close to over 1 million calculations. Now a computer will do that very quickly. You have pretty fast computers now. If you go to 1,000 by 1,000 matrix, I don't know if the computer could ever get done, or all the computers in the world, and if it could, you don't have to go much over 1,000. Okay? 1,000 factorial is a really big number, because That's really what you're looking at, okay? So my intuition tells me that's way beyond anything that computation could do. You don't have to go to a very big matrix to get a computation that would take a number of supercomputers, fastest computer in the world. If you had one for every particle in the universe, you still couldn't get it done in less than whatever number of years you wanted, in less than the age of the universe, okay? Totally impossible. But reducing a matrix and keeping track of the numbers you multiply by and whether you reverse rows, even with a big matrix, it doesn't take all that long, okay? You have a huge matrix, 1,000 by 1,000 matrix, any desktop computer would spit that one out in less than a second, okay? Just by doing the row reduction. All right? It's real easy to write a row reduction algorithm. Well, that's the idea, okay? It's a very efficient way to calculate determinants using the result that we get from elementary matrices. And the proof of the overall result just is a notation. If you got a bigger matrix, then you got to have an E1 through an EM. But you know that's going to be possible because you know you can do that. You've done it with up to 3 by 3 matrices. You know you can do a 10 by 10. Okay? Or an N by N for any reason. Okay? So you know it's going to work. So really here we have something very close to a proof of this idea. Determinant of a series of matrices that used to reduce is the reciprocal of the determinant of the original matrix. And the inverses have determinant. Product of the inverses has a determinant that's equal to the determinant of the original. And you see something about structure. They got this thing called LU decomposition, which unfortunately I can't go into because I find myself suddenly on this committee that's helping select the president, and there's a guy coming to room 130 just down the hall, and we're having a session for him in less than 2 minutes. So I gotta go.